Hello and welcome. Today is 27th of May. So we are going to continue our work with Solver, with Optimizer, and today we're going to talk about the nonlinear optimization, the GRG nonlinear, GRG multi-start options of Solver in Excel, and also we're going to talk about the evolutionary solver engines, and these engines are going far beyond the general Simplex linear problem engine, which we already dealt with for two lectures. So here's the deal. We are going to use the data solver. Let me open it. This kind of solver has the several options: the simplex linear problem option, the GRG nonlinear, and evolutionary solver. Inside each of these methods lies different optimizers, and simplex linear problem is just the method for solving linear problems. So the problems which are involving linear equations, when we have something like sums, when we have something like a multiplied b, or some product of two variables, and then we place everything inside a linear equation and use the linear programming solution to solve the system of linear equations given those constraints which we specify. So for GRG nonlinear solver, it's a little bit different. It allows us to solve problems where we have non-linearities inside. So our linear equation might contain some kind of non-linearity. What kind of non-linearity are we talking about? It might be the solution of non-linear equation, and the simplest non-linear equation. Let me or create the let it be x squared, and here is the variable x, and here is the variable y, and x might be some kind of let's say 50, and y will be this to the power of 2. And let's say that we need to solve the problem which finds the minimum of this function. We can, of course, we can solve it instantly, because the equation is quite simple, but this is just for an example. So we are opening our solver, and here inside the solver we have the nonlinear function, and we set the objective. We need to find the value of y, which is the minimum, by changing the value of x, and we select the GRG nonlinear and click solve, and it finds yes, in our 0 point the value is the lowest. Okay. Hello, Nazarene. I'm just continuing to talk about the non-linear solver. You will be able to listen to it later in YouTube. All right, so here's the simplest kind of problem, and we are implementing the solver which is using this GRG nonlinear technique. Of course, we can use different kind of problem, and let's implement this kind of problem in the form of y equals let's say minus x squared plus 4x minus or plus 2. So we need to find the maximum value here. And how can we find? If you remember from the mathematics class, we need to find the derivative of that, and we can do it quite easily 2x equals 4, so x equals 2 will drive the maximum value. So let's implement solver to prove that the maximum of this function is in point 2. And this point 2 gives us the value 2 squared plus 4 times 2 plus 2, so it will be somewhere below 10. Okay, so x, let us just place some value, and here we place that minus 1 times this value squared plus 4 times this value plus 2. So we have the y and we have the x, and let's use this value, set this objective to a maximum, given that we change the value of that. Okay, and place the solver, and it finds the solution instantly. The solution is about that 1999, and this is approximately 2, and the maximum value is 6. Okay, so that's what we obtained. Next, let's move to our tasks. So inside our tasks, we have the books. So inside our tasks in the information analysis, we've got three files. So inside, we opened the first file about the warehouse call stamp, and here's here we have the task to assign the number of workers, and this number of workers is up to 80. And let's say that you're working in a firm and you need to assign these 80 workers into 4 groups. Approximately each group should contain 20 people. They might be even, but it is not necessary. And you have to assign each worker to one of the 4 groups. The groups are naming like 1, 2, 3, 4, and we just implement this pattern 1, 2, 3, 4. But the whole idea of this task is that you need to maximize the qualification or the quality of work depending on the group which is assigned it. So if the worker is assigned inside group 1 as like that, so the value of 9, because he assigned to the group number 1, that's why it has he has 9 as the quality, and the quality will be maximized. But at the same time, if worker number 1 will be assigned to group 1, its own satisfaction will be this value only 1. And maybe worker number 1 will be more preferable to be assigned to group number 4 to get his satisfaction of 7, and with the slightly less quality of work 8. So we just need to divide that, and this is quality, this is quality, and this is satisfaction. Okay, so here we have our groups 1, 2, 3, 4 and 1, 2, 3, 4. The same goes to worker number 2, which now is inside group number 2. That means this worker has the lowest quality possible, because maybe it's better to assign the worker 2 to group 1. And the satisfaction is also on average, because here in the group 1 the satisfaction is 6. Okay, so here what we need to what we need to place. We need to place each worker in this satisfaction, and we need to quantify what will be the quality and what will be the satisfaction here. All right. The quality and the satisfaction. So the quality, let us create a couple of new satisfaction columns, and each column will have the horizontal lookup. Here the H lookup. We are looking the value assigned, and our table array will be this one for quality, and which kind of row index should we place? We should place some kind of so we try to place the value, let's say b3 plus 1. Okay, let's try to make it. And YNA, we're trying to maybe it's better for us to create names. Let's create names as the qualification. Okay, now we go to define name, and we define name as qual, and we define the next name as set. Define name set. Okay, so we define those names, and now we change that to comma qual. Will it work? Yes, now it works. The same is happening with the age lookup here in this function. We are looking at the value of the group which the worker is assigned to, and we select the table array set which we just created from the name, and we place the row index b3 plus 1. Okay, so check that the satisfaction here is 9 and 1, and here it is 0 and 6, which are the same as here. So let us move a little bit our values. We don't have those, so I'll just delete them. Okay, so here are the quality and satisfaction that which we obtained through our choice according to the group. All right, now as we have obtained the quality and satisfaction, we need to somehow calculate the total quality and the total satisfaction. And total quality and total satisfaction will be calculated as the sum of those values. Here they are. The total quality and total satisfaction are those values. Okay. Next, what we need to calculate is to find out what will be our function to maximize. We need to maximize the total value, and this total value is by definition. Maybe we need to multiply quality by 2, and this is the most preferable characteristic for the company. And for your assignment, you will need to change the quality to 1 and the coefficient before satisfaction to 2. So here we have the total, and it will be 2 times 379 plus 387. So now the total quality and satisfaction is 1145. Now let's try to solve this kind of problem, and then we will see that it is not optimal. So for now, let's use the data solver, and we set this objective for maximum, and we're going to change those variables assigned to. Okay, these are the variables which were changed, to which group the worker is assigned to. And then next we need also to implement the boundaries for these groups. We know that there must be only 4 groups. That means our groups should be less than or equal to 4. This is the first constraint. The second constraint, those groups are more or equal to 1, so they are between. And we need to implement integer constraint as well, because the groups are only 1, 2, 3, and 4, so they are integer. All right, so for now we have set 4 options over here, and in this kind of problem, as you can perfectly see, we haven't applied any nonlinear functions. So inside this problem, there were no nonlinear functions, only the characteristic which tries to change the values of quality and satisfaction over here. Let's implement the single option that we haven't been used yet, and this option is Evolutionary Solver. So we're going to use the Evolutionary Solver, and inside the Evolutionary Solver there are several options which belong to this method. And here the most important characteristic is mutation rate. So Evolutionary Solver is using a genetic algorithm to find out. So here's the function. Inside the function there is some kind of line. It might be local maxima, it might be global maxima, and to find this global maxima and not just to find the local maxima, we need to place different starting points inside. So we are placing those starting points, and then we try to manipulate them. And the mutation rate is how often will we manipulate them. In this particular case, it's not that how often, but which part of the population will be mutated, randomly changed. So for now, by default, the random part of our population which is changed is only 7.5%, which is so absolutely not enough. So we have to place the mutation rate to 0.5, and there is also the random seed, which allow you to change, and using this random seed, the points will be placed accordingly. You can place here any integer, and this integer will be the same. If this integer is the same for 2 computers, the result should be okay. Should be the same. So here in our task, we can use population size. This is how many points we place on the function to find, and the reasonable amount of points there might be from 50 to 100 for this task, because we have 80 workers. And here we also need to change some kind of the maximum time without improvement to maybe 3 or maybe 5 seconds. So let it be 5 seconds. So once we implement these options for our solver, it should produce some kind of solution. So if something is wrong, then we might change the convergence ratio. This is the difference between the solution and the result. And the larger this number, so maybe not 0.30 and 1, maybe this one, it will help the solver to find the solution faster. But if you make lower number here, the solution will be better, but it will take considerably more time to find it. Also, there might be one option require bounds on variables. Maybe if something is wrong, then you need to implement this require bounds on variables here. Okay, so for now, let's leave convergence rate and random seed and population size unchanged, and we set mutation rate and the maximum time without improvement to these numbers. Okay, so we have set that, and here we have some constraints, and we're changing these variable cells without any penalties, without anything. We just try to find the solution. So we can see here in our left lower part of the screen, it tries to solve some kind of the problem, and generally if we press escape, then there will be objective cell. We can see that the objective cell and the value there is constantly changing. I'm not sure that the recorder will be able to capture this, but it grows slightly, 1642 so far, and so on, and tries to be larger and larger. So the initial was 1145. Okay, so we have found this kind of problem, and we might keep the solver solution. And as we preferred, let's look at worker number one. So the worker number one, we initially thought that it would be better if worker number one will be working here in our group number 4 to get the quality of 8 and to get the satisfaction of 7, because 8 plus 7 gives the largest number, and quality is a larger value. It is more preferable for us because our resulting function values quality twice as much as the satisfaction. So the solver finds that out, and the worker number 1 assigned to group number 4. That means our worker will get this value over here and over here. So let's remove unnecessary conditions. Also here. So worker number 2 is assigned to group 1 to get the quality of 10 and get the satisfaction of 9. Obviously, it also maximizes those values. Okay, now let's count how many workers each of the group obtains. And now let us create the group. And in this task, we have had 4 groups, and we have had 80 workers. So let's find out how many of them. By the way, the task is this file, warehouse. So let's find out how many of them were assigned. And here we implement the count if. The range is assigned, and the criteria will be just group number. Okay. So far we can see that these assignments work already, and they are reasonable because in general we should have approximately 20 workers per group, and the boundaries we could have placed will be like from 18 to 22. This is all right, but we may try to find the better solution in terms of the number of workers. Maybe it will be better to bound the number of workers in each group from 19 to 21. So we limit only 19, 20, or 21 workers in each group can be placed. So let's do that. And this is really important thing for us to implement penalties. So how can we implement penalties? Penalty is the condition which we place based on our perception. And the penalty will be the logical if here, and the logical test here will be or. So what we need to do, if this value is more than 21, or logical one, this value is less than 19, then we implement value. If this is true, if this value is 18, then we place 1 instead we place 0. So we implement this kind of test as the logical condition here, and it will place the binary variable 0 or 1 in as our result. Okay, so here is 1 and only 21 is all right. It is within the boundaries that we have set. And if we have this penalty, then we should, how to say it, we should make the real penalty, not the only value 1, because we have the quality and satisfaction which are hundreds, and the total value is about 1000. So we need to get the penalty which is reasonable for the solver not to stick with this solution. Because if the penalty will be only 1, it doesn't matter for this, the total will be only 3 points less. But if each penalty is implemented, and the amount of this penalty, the how hard it is for the solver to bound within this solution, it will be really significantly better for solver to skip the solution if the penalty is large. So let's change this penalty for us to, let's say 1000. Let's say 1000. Maybe it will be like the sum times 1000. So here's the penalty, the overall penalty. And our total will be placed with the quality and satisfaction plus this value. So we subtract the value of penalty from the value, and we got the total which is really low. Then our solver should understand how to figure it out, how to make the groups even, and make our total value of positive. Let's try to do that. So for those who came, we are working with this warehouse problem. Our task is just to assign workers to the groups. Groups are changed from 1 to 4. These are the HLOOKUP functions. We implement two variable names. The qual is this rectangular, and for satisfaction we implement this rectangular. So pretty easy. We are trying to look at the value assigned at. We are looking at inside the satisfaction, and we return the value which is b3 plus 1. Okay. This is for satisfaction. How to create the name? We just select the whole boundary, go to formulas and click define name. And here the name, if we have selected quality like that, we click define name and it will appear the qual over here. Okay, so like that, qual. Here are just the sums of quality, sum, and here the sum of satisfaction. And our total is the 2 times quality plus satisfaction minus penalty. Okay, hopefully everything is good. Next we go to data, and now we implement the solver with these new conditions. Let's try to find the value which is satisfiable. Generally, the value will be lower than 1651, which was found without any penalties. And now, yes, we have found the solution, and the groups are pretty even from 19 to 21. Everything within the boundaries, and we have this total value. So this is the optimal solution for this kind of problem. And using solver, it's pretty easy. You can find the solution within seconds. And imagine that we were responsible for finding this optimal solution by hand. This is generally takes hours for us to figure out how to do it. So this was the first problem. And next, let's get back to the nonlinear solver. Nonlinear solver, as I have started to talk with the problem which involves nonlinearities inside the functions, and these nonlinearities might be overtaken with the nonlinear solver. All right, so let's open the file assign temp, this one, assign temp. This file over here. This one, assign temp. Okay. Let's open the file which involves us to implement the GRG nonlinear solver. So warehouse temp is our second file, warehouse temp. Okay, what do we see in this warehouse temp? We have two warehouses problem, and we have one warehouses problem. So we will start with solving one warehouse problem, and we will use the formula to find the distance from these two warehouses problem. Okay, so here's the distance, which uses the formula 69 times square root of latitude minus the latitude of the warehouse squared plus longitude minus longitude of the warehouse squared. So we will use the same kind of formula to find out where should our one warehouse be situated. The whole idea of this task is let's implement what is the optimal place where the warehouse should be situated to cover the shipments of these amounts from different cities. So let's imagine that here's the map of the United States, and here are some cities placed, and here are the coordinates of these cities, right? So we might calculate the distance between each city and the warehouse. So the goods are shipped from the warehouse to the city, and we are trying to make optimal placement of this warehouse to allow the shipments to be delivered faster and cheaper. So what should we implement over here? We will use this kind of formula. So we just copy this formula over here, and here is what we have: 69 times square between latitude and latitude, and square of this longitude and this longitude over here. So here we have the distances calculated between the warehouse and the city. Now let's calculate the total shipped distance. So if there are 15 shipments, so let's say that there are 15 cars though. So here they are multiplication of the number of cars times distance, and this will be the total distance which was driven by those cars. And here's the mean value which we are trying to on average there were that many shipments divided by the total distance. So on average the cars are traveling more than 1,000 miles. So warehouse right now in these coordinates is near Springfield, Missouri, and average distance is 1126 miles. Let's try to make this distance smaller, and to make it smaller we are using the Geogenome Nonlinear Solver, because inside our calculations there were square roots, and we need to implement this nonlinear solver. So we're going to set our objective as our mean value, like that, and we minimize the travel distance, and we minimize it by changing cells the distances. Okay, the distances or the total ship distance, but generally we minimize the distances between the warehouse. Set the Geogenome linear and try to solve this problem. Solution does not converge, so there might be some kind of option that we need to take care of. So which kind of problem we might encounter? Let's go to options and find the Geogenome linear. And here we can see that there is a special option which is not ticked right now. It is the use multi-start. So use multi-start allows us to start from different points and to try to converge from different points. All variables must have both upper and lower bounds. Okay, let's place the upper and lower bounds inside the variables, again inside the options. Yeah, okay, I understand what is happening. We need to change the variables, not the distances, but the latitude and longitude. Sorry about that. We need to change only the where our warehouse should be situated to these values. Options. Let's get back and require bounds on variables and solve it. All variables must be both. Okay, let's change our bounds. Latitude and longitude are not great, so we need to implement constraints on those values. So what kind of constraints might we implement on latitude and longitude? And if you remember, there should be values like more or equal to 90 for the latitude, less than or equal to 90, and generally they should be more equal to 0 at latitude should be less than or equal to 90. This is the constraint. And longitude should be less than or equal to 150. So these are reasonable constraints for changing in latitude and longitude. And maybe everything will be okay to find out the solution. 86 and 147. 86 and 147. Okay, but why didn't the solver the distances? The distances are not calculated. So we need to implement the 69 times square root of latitude minus longitude f4 squared plus latitude plus longitude minus longitude squared. Okay, hopefully. And we need to make those values f4, and here again f4. Okay, now we have the mean value which is larger, and we implement solver, and our solver should find the solution. It finds the solution 1125. So hopefully it is the best possible solution, because all in all it tries to change, but it finds the same kind of solution. And maybe we start from different values, from 1 and 1, starting from 7,000, and try to solve it again, and it again finds the solution which is already stated over here. So the best solution possible, depending on which kind of latitude and longitude we check, it finds that. Alright, so we need to reconnect. Our 40 minutes is up. Please reconnect.